Assalamualaikum warahmatullahi wabarakatuh. So my name is Nur Ainul Mardia binti Mat Salinia and my matrix number is 73012. So for this question, we have to find the room temperature response using Euler method and the midpoint method. So let's go. So I include the objective for this question, which is we have to determine room temperature at the T equal 0.C using Euler method and the midpoint method. We also have to calculate the relative true error and compare the accuracy of the both method. So let's get started. So at this point, we have to show step by step to calculate the final room temperature using Euler method. So as you can see here, the final temperature for T is 187.2. Meanwhile, for the midpoint method, we can see the final temperature is 160.9776. You can see the step by step to find the final temperature at this point. Okay, next we move to the next slide, which is MATLAB verification. We have to use MATLAB to find the room temperature. As you can see here, the answer is 187.2. 187.2000. Same goes to the Euler method. Same goes to the midpoint method. The answer is still same, which is 160.9976. So there's no difference if we do MATLAB and the manual calculation because the answer same. Next, we have a relative error, which is we have to find the percentage error for midpoint method and Euler method. And then the answer for the Euler method is 12.1360%. And for the midpoint is 3.5717%. So we move to the next slide. Next, we have an accuracy comparison. As you can see here, the aspect is order of accuracy, which is Euler method. Get the first order, meanwhile midpoint get the second order. But for the stop use, Euler method beginning of interval, meanwhile the midpoint method is midpoint of the interval. And the accuracy is lower for the Euler method, meanwhile the midpoint get the higher. And the relative true error is large for Euler method, but the midpoint method get the smaller. In conclusion, both methods successfully solve the differential equation, and the MATLAB result show the match to the manual calculation, and the midpoint method produce a smaller relative true error and also is more accurate than Euler method. So that's all from me. Thank you.
Hi, Assalamualaikum. My name is Muhammad Aiman Hakim. So, we move to the chapter 2. For this question, I use the Newton-Raphson method to estimate the diode operating voltage. First, I define the function as Fv equals to Ve 0.5 minus 5 and its derivative because Newton-Raphson require both the function and its derivative. For the manual calculation, I started with the initial guess of V equals to 2.0. Then I substitute the value into the Newton-Raphson formula and repeated the calculation until the approximate relative error was below 0.05%. After a few iterations, the voltage coverage to 1.9172 voltage. To verify the result, I also implemented the same method in MATLAB. As shown in the common window, MATLAB also converges to 1.9172 voltage after only 3 iterations, which confirm that the manual calculation is correct. This shows that the Newton-Raphson method converges very quickly and provide high accuracy. Next, I solve the same equation using the bisection method. For this method, I selected initial interval from 1 to 3, where the function change signs. In the manual calculation, I calculate the mean point of the interval, evaluate the function value, and select a new interval based on the sign of the result. This process was repeated until the required error tolerance was achieved. The final estimate voltage obtained was 1.9172 voltage. Then, I verified the answer using MATLAB. The MATLAB result matched the manual calculation and produced the same final voltage of 1.9172 voltage, but it required 12 iteration to converge. Compared to the Newton-Raphson, the bisection method is more stable because it always covers if the correct interval is chosen. However, it covers more slowly. So, comparison and accuracy. Newton Raphson is faster and more efficient because it only needs T iteration to get the final value of 1.9172 voltage with a very small error. The bisection method is slower because it needs 12 iteration, but it's more stable and reliable because it uses an interval. In terms of accuracy, both methods give the same answer, 1.9172 voltage. So, both are accurate to 4 decimal place. For a real-time everyday circuit monitoring system, Newton Raphson is more suitable because it is faster, while bisection is better when the initial value is uncertain.
To start off, let's look at the problem we are trying to solve. In this slide, a deeper sea submersibly lost a packet of temperature data at 2.5 hours marked due to a software glitch. Our job is fill up in the gap using the surrounding data points. Since we want a higher accurate third order interpolation, we choose the 4 nearest data point hours 2, 3, 4 and 5. First, we are solved this using the Newton divider different method. As you can see in our manual, solution on the right, this method built a step-by-step table to difference. We use those table value as a coefficient to build our polynomial, which given us an estimated temperature of 25.85 degrees Celsius. To double check our work and automate the process, we wrote a MATLAB script is used to nest loop to build that same different table automatically and give us the exact same results. Moving to this slide, we wanted to solve the exact same problem but using a completely different mathematically approach. The Lagrange interpolation method, we are using the same target time of 2.5 hours and the same 4 data points. Instead of building a step-by-step table like Newton, the Lagrange method calculate individually weight like labeling here as L0 to L3 for each data point. We multiply each temperature by its weight, add them all up, and as you can see at the bottom right, we get the exact same answer, which is 25.85 degrees Celsius. For our MATLAB coding for this method is shown at the bottom. Instead of matrix table, is use a loop to calculate those fraction weight dynamically before summing them up. Finally, let's look at this slide to compare both methods. While both are approaching giving us the exactly same temperature results, they are handling data very different when it's come to flexibility. Imagine the submersibly suddenly stream a new data point. If we are using Newton method, it's incredibly efficient when we done. We don't have to redo any old math. We just add on a new line to our existing table. This make it perfectly for a large and continuous updating data. However, the Lagrange method, on the other hand, is not flexible. If a new data point is added, the entire formula breaks and we have to recalculate every single weight from scratch. To summarize our table on the right, both methods are perfectly accurate, but Newton method is much better expanding the data, while Lagrange is best to keep for a small and fixed data set.
Hi, Assalamualaikum. My name is Raja Aizat Hazim bin Raja Khairul Azli. My number metric is S73034, and today I would like to present about chapter 6, which is numerical integration. So this is the question 6.5. Okay, so first we solve the n equals to 1. So first thing first, we must find the h. The formula of the h is h equals to b minus a over n, where n is 1. So we got So we got the h for n1 is 2, and we apply the formula where b minus a over 2n multiply with fa plus 2 summation fa plus ih plus fb. Okay, so we move to the b where we find the rhomboid integration. Okay, now we move to calculate the percentage true error. Okay, the true error for this question is 2.6662. Okay, so this is our MATLAB code. Okay, so the comparison. Since the percentage true error of rhomboid integration is 0.1662% is smaller than that of the trapezoidal rule with n equals to 4, 0.5258%, rhomboid integration provides a result that is closer to the true value. Okay, in conclusion, the integral was calculated using MATLAB and manual solution. Using the trapezoidal rule, the approximation obtained were 2.4778, which is n equals to 1, 2.5980, n equals to 2, and 2.6480 for n equals to 4. As the number of subintervals increase, the results become closer to the true value. Rhomboid integration further improved the result and gave an approximation of 2.6664. The percentage error was reduced from 0.5258% to 0.1662%. Therefore, rhomboid integration is more accurate for this problem while still being efficient to use. That's all from me. Thank you.